I'll invite Dr. Fabrizio Romano to, Fabrizio, you can start sharing your slides while I introduce you, if you would like. Dr. Fabrizio Romano is a senior researcher at the Istituto Nazionale di Geofisica e Vulcanologia, in Italy, and a member of the Global Tsunami Model. His research is focused on the rupture processes of tsunamigenic earthquakes, particularly through tsunami numerical modeling and the inversion of geophysical data. And his work also extends to tsunami hazards and warning systems, and he's one of the co-founders of the Italian Tsunami Warning Center. With that, Fabrizio, right now we're seeing your conclusion slide.
Okay.
Great, I will pass it over to you. Thank you very much.
Now, can you see? Because I don't know if...
Okay. Looks great. Yeah.
Good. Thanks, Malaika. No worries for the pronunciation of Italian name of my institute. It's a pleasure for me to be here, and thanks for inviting me. And good evening or good morning to everyone, depending on your local time. So I'm going to present a recent study that I did with my colleagues from INGV and other institutes about the 2025 Kamchatka Tsunami, and some features about the tsunami that can be explained by the complex seismic rupture. A short introduction, sorry for this repetition, Zoe already explained very well the mechanism of tsunamigenic earthquakes, but the same, allow me to repeat, the subduction zones in the world are the ones that host most of the seismicity at the global level and host the large seismic events, also the mega events. In particular, for example, the Sumatra 2004 was a magnitude 9.2, and this kind of events, if occur in the sea or close to the sea, has the potential to generate a tsunami that can propagate also over the ocean at transoceanic distance. Here there is a simulation showing the 9.2 Sumatran Andaman earthquakes. Of course, if the tsunami is big, can have very, very dangerous impact with a lot of fatalities, people missing, at the capacity to destroy buildings, to damage the ports, and also nuclear power plant, like all of you for sure remember in 2011 for the Fukushima accident. Now, the 2025 Great Kamchatka earthquake was an earthquake occurring last July with a magnitude 8.8, the equivalent in terms of seismic energy of more or less 15,000 Hiroshima bombs, just to have an idea of the energy that this earthquake can generate. It was due to the mechanism, subduction mechanism, where the Pacific plate subducts beneath the Okhotsk microplate, and the earthquake occurred along the subduction interface between these two plates. And this is the sixth largest event occurred since the beginning of the instrumental era. And the tsunami that was generated by this earthquake was a tsunami that traveled all over the Pacific Ocean. Here there is a movie, and this is the propagation of the maximum wave weight modeled by NOAA, that after 21 hours more or less reached the Chilean coast on the other side of the ocean with respect to the origin area. This tsunami was important, and it was followed by, the earthquake was followed by a timely tsunami warning message issued after a few minutes by the Pacific Tsunami Warning Center. We can say that the warning from Pacific Tsunami Center was fast and efficient, and it was timely sent to the 46 countries around the Pacific Ocean. But while the tsunami message warning was issued very, very fast, We observed while the time was passing that the tsunami generated by this event was overestimated, fortunately, I would say, with respect to the tsunami forecast produced by the warning system. Here there is to the left panel a figure showing the forecasting from the Pacific for the Pacific Ocean. In the middle, the same, but produced by the Japan Meteorological Agency. And to the right there is an histogram showing how the amplitude forecasted by these systems are with respect to the observations that we measured, for example, at the coastal tide gauges. And we can see that the observed ones are generally smaller with respect to the warnings issued. So motivated by try to understand this discrepancy, we studied this earthquake by using a different kind of observations. First of all, tsunami observations from dart buoys that recorded the tsunami very well deep sea in the Pacific Ocean, and from the tsunami measured by the SWOT satellite that measured the sea surface 8 in the Pacific. I have to say that this second measurement is is valuable for infer information from the tsunami genesis process, and this is a not so common observation when a tsunami occurs, because we have to find the combination of time and the dimension of the size of this the tsunami event, because the satellite has to pass exactly when the tsunami waves is passing in the ocean. So we were lucky in this sense, and we also used cosmic deformation observations from the Sentinel-1 satellite INSAR data for both the ascendant and descendant component in line of sight, and two geodetic cosmic offset from the GNSS network for stations located in Kamchatka. Then we inverted a multiple data set combining tsunami and geodetic data that is important for tsunamigenic earthquakes, because these two different kind of data, tsunami and geodetic, are complementary because the tsunami data are able to resolve very well the features of the tsunami source in the sea, and the geodetic data are very well to reproduce the rupture information, the rupture features for the part of the rupture that is close to the land. Here we parameterize the fault surface through the SLAB2 models from USGS with quadrilateral element of 25 by 25 kilometers. And we compute a geodetic Green's function by using the analytical formulation by Nico and Walters. We use the same approach to compute the initial condition for the tsunami, and to propagate the tsunami, we use the Jacques model that take into account the dispersive behavior of the tsunami waves. And we did this on a bathymetric model with a spatial resolution of 1 arc mean. After generating the tsunami Green's function, we perform a joint inversion using an global optimization method that is the simulated annealing, exploiting the linear combination approach of this Green's function. And we invert this data for estimate the slip model, that is the slip, this location, and the rake angle of this location. We use as a priori information a rupture velocity along the fault of about 2 kilometers per second that we took from the USGS finite fault model that Zoe showed before. And we found an average slip model from the entire ensemble of the Explored 1 by the inversion that we prefer with respect to the best one, because we want to avoid any possible outliers in the models that correspond to the minimum, to the global of the cost function. This is the model that we found after the inversion, that is characterized consistently with the USGS model by a unilateral rupture propagating from the epicenter in southwest direction. We individuate three main asperities, one that is a moderate slip close to the epicenter, and the other two that are in the middle and to the south of the fault surface with the peak slip of about 17-18 meters. And the rake is consistent with the convergence direction of the relative between the two plates. For what concern the comparison between the observed data and the modeled one, this model predict very well both the tsunami and geodetic data, as you can see in these figures. And I want to focus on the SWOT modeling, where we are able to reproduce with the JACULS code also the dispersive behavior of the tsunami propagation in the open ocean. Now we focused on two things. First, the comparison of the rupture model of the 2025 event with respect to the 1952 one. And we observed that the 1952 with the 2025 is in a sense complementary, or they are also very similar. In particular, the first model of the 1952 obtained by far-field tight gauges suggested that these two ruptures are complementary. With the 2025 that cover the shallowest part of the subduction, and the 1952 the deeper one. But a revised model of the 1952 used the sediments data in the near field of the tsunami, suggests a possible different mechanism, different pattern of the rupture, and in this second case the two ruptures are almost overlapped. Remain some uncertainties with respect of this comparison, but we can the same state that the 1952 the time passed from the 1952 is able to recover the interseismic coupling that and generate a possible other earthquake like like occurred for the 2025. The second aspect that we investigated with this study is as I said at the beginning, the limited impact of the tsunami associated to this earthquake, and we can divide it into this impact in the far field and in the near field. In particular, in the far field, the impact was smaller with respect to the one occurred in the 1952. This is due probably to the limited shallow slip that occurred in this earthquake, and that can be translated in a smaller tsunami potential energy that we computed by considering the initial water displacement, that is from 5 to 10 times smaller than the 1952. For what concerns the near field impact, on the other hand, we can say that the impact, if we consider the maximum run-up measured by this earthquake, is similar to the 1952 event. This is due probably to a trade-off between the smaller potential energy associated to the 2025 event, but at the same time a shallower rupture with respect to the 1952. And in the combination of the trade-off between these two ingredients make the run-up comparable, about 15-20 meters. To conclude, I want just to highlight a couple of points. we estimated that the rupture process or the tsunami source for the 2025 Kamchatka earthquake, and we individuated a tsunami source that can be interpreted as a partial rupture of the subduction interface with an overlapping probably with the 1952 events. We found that there is a limited impact of the tsunami in the far field due to the shallow rupture of the source, and a comparable impact in the near field. But this is the first Pacific-wide activation for the Pacific Tsunami Warning Center after the Japan tsunami in 2011, and demonstrated the system that it worked very well, even if the forecasting was overestimated. I would highlight that this is a conservative choice, what we observed in this case, that saves life for sure. But the risk here is that there can be an overreaction when you have a very big conservative situation. How we can deal with this kind of problem? For sure, by reducing or better quantify the uncertainty that can be due, for example, by using new sensors, or by introducing information resulting from, for example, data inversion. And last but not least, I want to highlight the fact that such a kind of study, in particular the rupture process, is important, is crucial to inform the seismic model when we are dealing with the probabilistic tsunami hazard assessment, like we want to do in the Global Tsunami Model. Thank you.
Thank you so much, Fabrizio. Similarly, you already have questions in the chat. That was a great follow-on, I think, too, from Zoe's presentation. We will have other questions at the end.